osmotic pressure, right? So let me just go over lowering of vapor pressure again, just so you can understand elevation of boiling point as well. So elevation of boiling point was the second colligated property. And what was colligated property? Colligated property were these guys, they were affected by the number of solute particles, and they did not depend on the nature of the solute. These properties depended on the number of solute particles or the concentration of the solute or the moles of the solute, not the nature of the solute. Solute koi bhi ho, but kitni amount mein hai, that will affect these properties. So let's start with elevation of boiling point, right? And while I'm explaining elevation of boiling point, I will go over the first property, which was what? Lowering of vapor pressure, right? Now, if you remember that this right here was the solvent without any solute, right? So this was the solvent without any solute, and the solvent particles on the surface, they will have a higher energy, so they will escape as what? Vapor, and they will start increasing the vapor pressure, right? This was happening when you had no solute. But if I add the solute now in my solvent on the surface, I will also have some solute particles. Let me just put them in pink, right? So you will now have some solute particles on the surface. Now, since you have solute particles, this right here is my solution. It is basically my solute plus solvent, right? So now, since you have a solute on the surface, the escape of the solvent particles will become difficult. And now the surface area now, do you see, has decreased for just the solvent. So now can I say when you add the solute, the vapor pressure decreases, right? Because आपका surface पे अब solute भी है, so that will decrease the vapor pressure. Less particles, less solvent particles will now be escaping as vapor, right? Because the surface is covered with solute. So we know that on addition of solute, the vapor pressure tends to decrease. And you can see this phenomena of vaporization or evaporation. It is very different from boiling. This evaporation or vaporization is different from boiling. Why and how? Let's see. We've done this before also. I'm just going to go over it again. Evaporation or vaporization, as you can see, only happens at the surface. So this right here is a surface phenomena. This happens only at the surface. This is a surface phenomena. Whereas this happens throughout the liquid. This happens throughout the liquid. Vaporization happens at a range of temperatures. This can happen during a range, like doesn't have to be at a fixed temperature. Whereas boiling happens at fixed temperature, which is your boiling point, right? So now we understand this, and we know that boiling, we've done boiling before, and we know that boiling occurs when your vapor pressure will be equal to the outer atmospheric pressure. Let's assume we do not have a lid here. We do not have a lid, okay? So when the atmospheric pressure, which is trying to put a pressure downwards, is equal to the vapor pressure, when these two pressures would be equal, what will happen? That all throughout the liquid, the particles will gain energy, will be at a higher energy, and now they will try to escape as vapor. So when your vapor pressure is equal to the outside atmospheric pressure, what happens? Boiling occurs, right? Now, since you added the solute, what happened to the vapor pressure? When you add the solute, you know, when you add solute, the vapor pressure tends to decrease, right? The vapor pressure tends to decrease. Now, if the vapor pressure is decreasing, that means that it is becoming vapor slowly, like it's not happening rapidly. You're not getting vapors. One second. You're not getting vapors rapidly, right? You're not getting vapor particles rapidly. One second, guys. Yeah. So if the vapor pressure has decreased, so they're not becoming gas as readily as they were earlier without you having to add the solute. तो पहले तो ज़्यादा जल्दी vapor बन रहा था, but अब नहीं बन रहा because you've added the solute. So you know, since solute decreases the vapor pressure कम हो गया. That means it's taking more time to become vapor. So can I say that the boiling point will increase? Or the boiling temperature will increase, or the boiling point will increase. Why? Because it's becoming vapor very slowly now. So you will have to give more energy for it to become what? Vapor. So can I say in that case, if you have to give more energy, what is happening to the boiling point? The boiling point will increase. And let's see this as a graph. Let's see this as a graph of vapor pressure and temperature on the x-axis. And we know that boiling occurs when the outside atmospheric pressure is equal to the vapor pressure. So let me say कि भाई ये आपका mark हो गया for 1 atmosphere, right? So now when you had the solvent alone without the solute, let me say it was this guy right here. So can I say at 1 atmosphere, this was this temperature? Let me call this TB naught. So can I say my solvent was boiling at TB naught, right? The temperature was B naught for the solvent alone without the solute. ठीक है? अब जब आप solute डालेंगे और solution बनेगा, so you know that the vapor pressure will decrease. So can I show a decrease in vapor pressure? Can I call this solute plus solvent, or can I just call this the solution? Right? And now, okay, just 1 second. This right here, if you see, do you see the decrease in vapor pressure? Let me just draw it like this. Okay, do you see a decrease in vapor pressure when you added the solute? This purple line that shows the solution. And now if you see 1 atmosphere pe, it is requiring more temperature. So the boiling of the solution now, do you see, occurs at a greater temperature? Do you see this difference between TB naught and TB? This TB is the boiling point of the solution, whereas TB naught is the boiling point of just the solvent without, pure solvent without the solute. And now do you see that there will be a change in temperature? Can I call this delta TB, right? So do you see that the solution boils at a higher temperature? So do you see elevation of boiling point happening once you add the solute? Okay. Now you know that elevation of boiling point is a colligative property. So it will not depend कि आपने कौन सा solute डाला है, but it will be dependent on how much solute you have put. So can I say that the elevation of boiling point, or can I say the elevation of boiling point, can I call this delta TB? Can I say it is directly proportional to the number of moles of the solute particles? Right, because it's a colligative property. Now nature pe to depend nahi karta, it depends on what? The number of particles, right? Anyway, so now if I want to find delta TB, right? So move on to the next page. Delta TB is basically the difference in the temperature. So I'll say bhai, it will be what? TB, which is a greater value, minus TB naught, where TB was the temperature or the boiling point of the solution, and this was of the pure solvent, right? Now we know that this is gonna be the elevation of boiling point, and you can find delta TB by this formula. You also know that delta TB is directly proportional to the molar concentration. Can I say this will be equal to the molar concentration of the solute? Now I'm using what here? Molar concentration. So I'm using what? I'm using molality, which is denoted by a small m. And what was molality? Molality was basically the number of moles of something, in this case is the solute, over the mass of the solvent, which was how much? How many moles of solute you have per kilogram of solvent. That was molality. We have done this before. Let me just find it for you so you can recall. Molality. Molality was the moles of solute over the mass of solvent. So how much solute you have, how many moles of solute you have per kilogram of solvent, right? So that was molality. So now here we are using the molality, and we know that the delta TB will be equals to the molar constant or the molality of the solute. So now if I remove the proportionality sign, it will be KBM. This is a constant. And this right here is called a boiling point elevation constant. This is called what? Boiling point elevation constant. This is also known as molar elevation constant. This is also known as ebullioscopic constant. Right? Now, you know that this guy is the constant. How to calculate KB, I'm going to do that in the end. All right. Now let's see. You know that M is molality. This is molality, which is basically what? Moles of solute per kilogram of solvent. Right? So let's see. You know that when we're taking solute and solvent, there are two things, right? In a solution, we always take one. If I say N1, so this is basically the moles of solvent. And the second component is always the solute, right? The first component is the solvent. The second component is the solute. Anyway, so now let's move on to the formula that was delta TB is equals to KBM, right? Now you know that M is basically molality, which is moles of the solute. You know how do you calculate the moles? Moles is mass upon MR, right? And mass kis cheez ka? Mass of the solute, which is component 2. So can I say W2, weight W2 upon MR is capital M, M2, right? So I can say that this is this. So delta TB is equals to KB, and M, can I replace M with moles upon kilogram of solvent? So can I say moles would be W2 upon M2, where W2 is the mass of the solute and M2 is the molar mass. So this right here is mass of the solute, and this right here is the molar mass of the solute. Okay, now upon kilogram of solvent. Ab solvent, for instance, agar मैं कहूँ कि the solvent that I'm taking, which is basically component 1, right? So if I say कि भाई in 1 gram of W1, ठीक है, but आपके पास किलोग्राम है, सही है? तो ये अगर मैं कहूँ कि this was in 1 gram, so what will I say कि भाई 1000 gram में कितना होगा X, right? So can I say that the per this kilogram upon kilogram of solvent, can I write this as 1000 upon W1, where W1 is basically the mass of the solvent, and this 1000 is basically 1 kilogram, right? So this becomes my formula. All right, so it will be delta TB is equals to KB, where KB is the boiling point elevation constant, times W2 times, which is W2 is the mass of the solute, times 1000 upon M2, which is the molar mass of the solute, times W1, which is basically the mass of the solvent. And then I'm going to take M2 that side. So it's going to be M2 is equals to KB times W2 times 1000 upon delta TB times W1. So basically, I can find the molar mass of the solute through its colligative property, right? So I can identify things based on I can find their molar mass, and I can identify amino acids, proteins, polymers. I can identify all these things on the basis of their colligative property, right? And you see that if you know the elevation and boiling point, you can use that to basically calculate what? The the molar mass, and to identify basically what proteins, polymers, or any other compounds for that matter, because you can find their molar mass. Okay. So I'm going to keep each topic as a short video. So I'm going to just